So we're going to discuss some of the recent, or maybe not so recent, progress of query complexity. In particular, we want to study the relationship between deterministic, randomized, and quantum query complexity. So to start with, let me just briefly review what are these complexity measures. Although very basic, you probably are familiar with, but let's just do a quick review in case. So the deterministic query complexity of a function f. So here we will be interested in Boolean functions whose domain is the entire Boolean cube. So the total functions. Deterministic query complexity will just be the minimum depth of a decision tree that computes a function. And when we discuss randomized algorithm with bounded error, we are talking about a randomized decision tree, meaning a distribution on decision trees. And in the end, a random decision tree should output a correct value of probability at least 2/3.
For every input.
For every input, yes. And then the cost of your randomized decision tree will be the largest depth of any decision tree that is on the support of your distribution. And then for zero error randomized query complexity, so again, we're considering a distribution on decision trees, but only on those trees that computes your function correctly. And now the cost of your decision tree will be the expected number of queries on the worst input.
So if they can ask you to just draw a decision tree for somebody who's never seen one, just draw one decision tree.
Okay. Sure.
Somewhere.
Expected number of queries. And the decision tree would just look like a tree, of course. And inside node is labeled by a variable. So that is the variable you want to query. So starting from the root, say you want to query x2, the second variable, and depending on the value of x2, whether it's a 0 or a 1, you go to the other the corresponding child. So say if it's a 0, you query x1. If it's a 1, you query x3. So on. So you can go on for a few more steps, but in the end, you will reach a leaf. And the label on the leaf is what you're going to output by this decision tree. Okay, so that's like classical query complexity. And then we also have quantum query complexity, whose definition is a little bit more technical, so we will defer its definition to the later part. And when we discuss query complexity, when we study the relationship between different models of query complexity, we inevitably encounter some other complexity measures. For example, the certificate complexity. So in particular, in this talk, we will encounter the zero certificate complexity, our function f, one certificate complexity, our function. So let's be precise. If you have an input, we say that a set, index set, certifies x if for any input that agrees with x on the variables indexed by the set, they also have the same value of the function. So fixing the variables inside this set as we also fix the value of fx. And then the zero certificate complexity of our function is to take the worst input x such that fx is a 0. So that's what 0 certificate here means. And then, oh, sorry. And then we want to take the minimum size of a set, minimum set that certifies the input x. Okay. So analogously, we can define the one certificate complexity. Okay.
So maybe it's good to say that these are all, baby analogs of, familiar, Turing machine or circuit complexities, right? I mean, the deterministic one, probabilistic algorithms like BPP and ZPP for the zero error and certificate complexity are the NP and co-NP.
Yes.
Right?
Yes. Yes. Okay. So these are analogs. We have like complexity classes in classical models, in like Turing machine models. But then we will also have some combinatorial measures like the block sensitivity and sensitivity. Well, sensitivity of the input is just the number of variables by flipping which you also change the value of your function. And the block sensitivity.
You want to say what the sensitivity of the function is? But
Yes.
okay.
But let me first define the sensitivity of an input and block sensitivity for input. And the block sensitivity is just a generalization of sensitivity. So now you can not only flip a single variable, but you can flip a block of variables. So the block sensitivity of an input will be the maximum number of disjoint blocks of variables. Such that flipping this block of variables, you also change the value of the function. And then the sensitivity of a function.
All the bits of the graph or some of the bits?
All the bits.
All of
them.
it, but different then, right?
I guess. Yes. Yes. So you want to flip all the bits in that block. And then sensitivity of your function is maximum sensitivity of the input over all input. Analogously for block sensitivity.
I like to think of sensitivity as like a discrete continuity measure. I mean, it doesn't change much locally at every, I mean, if it's small, it doesn't change locally at every value of the cube.
Mm-hmm.
So it's sort of.
Yeah. Okay. Well, then, two more measures. Let's see.
Yeah. Commutative. Let's talk about
Yes.
Yeah, you might want to.
Anyway. Okay. Okay. So like two more. Just two more measures. One is the degree function. So here the degree means the total degree for polynomial over reals. So the parity function will have degree n. And finally, the spectral sensitivity. It might be unfamiliar to some of you, for which our diverse definition as well. Okay, so these are the complexity measures that we will encounter.
You are going to define it later.
Yes.
Okay, good.
So when we move on to the quantum query complexity part, we will define the spectral sensitivity. Okay, so these are the complexity measures that we're going to encounter. So now let's start by comparing the power between deterministic query complexity and zero-error randomized query complexity.
So for none of these notions, there is a measure on the discrete hypercube. All of these are probably except the spectral sensitivity, which you haven't defined. But
What are you asking?
there is, for none of these notions, there you consider like the uniform measure on the discrete hypercube.
No, it's worst case. It's all worst
Like
case. It's
everything
fine.
that's written.
Everything is worst case, yeah. Yeah. Like in most of complexity theory. You can, I mean, people study, I mean, the randomized is, you know, by minimax, maybe it will come, you know, by minimax theorem, you can express some of the, you know, randomized complexity measures as a distributional one. So you can pick a distribution, look at the average cost, but you cannot pick the uniform distribution, maybe a weird distribution.
Like for complexity theory, the uniform distribution doesn't tend to play.
Not directly, no.
Okay.
Okay. Any other questions? So here we want to compare deterministic query complexity and the zero-error randomized query complexity. And we first state the Deasy theorem, which says that for any total function, its deterministic query complexity is upper bounded by its zero-error randomized query complexity squared. So this is due to another very well-known result that has been, I think, proved by many different authors independently. It says that the deterministic query complexity is actually at most the zero certificate complexity times the one certificate complexity. So that can be phrased as P equals to NP intersect co-NP for the query model. And in fact, this also holds for like communication model. The proof is like one line. Let me write it down. What you will do is you will just query a certificate until you know fx.
Okay, how many didn't see this proof? Just my, okay. Okay.
Great, then.
Okay, good. No, I just wondered what it is. Also an audience online.
Okay, so here a zero certificate, but a zero certificate S should mean a minimal certificate. It can be used to certify any input, doesn't matter. the point is that S has size at most the zero certificate complexity of a function. And then the claim is that after at most one certificate complexity times of iterations, you will know fx. Why? Because when one certificate satisfies for any input, any one input, then this one certificate must intersect the zero certificate S. So therefore, by querying the zero certificate S, you must have queried at least one variables in any one certificate. So reducing the one certificate size by one.
Is it clear to those who haven't seen why they must intersect? Otherwise, you could force the input to be both a 0 and a 1, but if they were disjoint.
Yeah. Okay. Okay. I guess that's the proof. What I want to make a comment here.
You can write for the video that this is non-empty intersection.
Oh, yes. Okay, so here I want to make a comment. So using basically the same argument, you can also show that deterministic query complexity is at most the zero certificate complexity times the block sensitivity. You can also show that deterministic query complexity is at most degree of your function times the block sensitivity. So using basically the same proof. Okay.
But it's asking any questions. Ask if something is unclear.
Okay. So that's the upper bound. The question is.
So is it clear to everybody why it implies a zero error bound?
Wait, it's clear why this theorem is true, but what?
Oh, I see.
It's supposed to be clear why it implies the first theorem.
Yeah, it's supposed to be clear.
Hold on. This. So give us a second.
Sure. Well, so R0 just means zero error randomized query.
Yeah.
So you have a randomized algorithm but cannot make error.
So every answer it gives is correct. So it's in particular it certifies the value it gives. Every path in this zero error tree is a certificate. Yeah.
Yes. Yes. So that just justifies the result, this upper bound. Yes, so of course now the question is whether this quadratic separation is whether this is achievable. So do we have a function that actually have a quadratic separation between these two measures? So this was actually a long-standing open problem before.
Maybe give a very simple example where it's like much larger, like.
So I guess it's the canonical example. You have this recursive and/or tree.
It's not a decision tree, it's a formula.
Yes. So AND gate, OR gate, AND gate, OR gate, alternating. And in the bottom layer, every while is connected to a fresh variable. Like this.
That defines the function.
Yes. So this defines a function. And deterministically, you have to basically query all the variable in worst case. But
so you can write if this is f and there are n variables, d of f is n for this one.
Yes. Yes. So that says height is d, depth is d. Yes. So deterministically, in the worst case, you have to query all the variables. Where you think, if you think about it, you realize this. And for random algorithm, somehow you can take the advantage of this alternating structure. So let's just, for example, say here its output is 1, meaning these two wires should give you 1. But then that means when you evaluate this OR gate, at least one of them will be a 1. At least one of them. So a random choice will give you like probability of half finding the correct path. And then you don't need to evaluate the other.
So you get some Boolean improvement. You get some constant to the power d instead of 2 to the power d.
Yeah.
Yes. Yes. So actually, that result was proved by Avi.
But the result is that it's tight. The upper bound is obvious.
Yes. To prove the tight lower bound, which says something like the deterministic quadratic complexity is at least the randomized quadratic complexity without error raised to power of, I don't remember, maybe 1.3 something.
Yeah. Just as this algorithm, this recursive algorithm is exactly optimal for this problem.
For, I guess this is almost like recursive majority.
Yeah.
The recursive majority gives a weaker gap.
But in terms,
It's a bigger gap than the recursive majority.
yes.
For recursive majority, it's also known what's the best exponent. I'm just curious.
No, but it's known that it's superlinear. Yeah, it's some other constant bigger than 1.
Sure.
It's not known what the optimal is because it's not true for recursive majority that you could you could go in one. I mean, it cannot follow the formula because its majority is not a read once kind of object. So, I mean, the variables are not
the optimal constant and the exponent is?
Yeah, for this, yes. For this, it's not exactly what the optimal constant.
Yes, so maybe if I ask you to guess, what is the optimal exponent? You would
In and 2?
Okay.
Guess that.
Yes. I think like this is actually the largest separation for over 30 years. I think Avi actually, Sachs and Avi actually make the conjecture that this is the largest separation. And then on finance, bodies belongs V, Sansa, and Smotrov. They prove that, well, the quadratic separation is achievable. And this is the result that I want to discuss. This result uses the technique called pointer technique.
It's for the same functions or for a different function.
Different function. So
There exists F, yeah.
yes.
The thing building on top of Goose, Pitasi, Watson, or
Yes.
Ah,
That's it. Yes. I want to tell you this pointer technique, first introduced by, as you said, Goose, Pitasi, and Watson, motivated by other problems. So this technique, although looks like a small trick, but it's actually very powerful. It motivates a lot of progress in some of the longest open problem in computer science, in theoretical computer science. So let me just tell you what is the function that exhibits this quadratic separation, and then I think you will see what this pointer means. So here we are going to arrange the inputs, the data into a 2n by n grid. And we will require that the one instance, so the inputs that has fx equals to 1 should have some special structure. In particular, we want to embed a complete binary tree into this grid. So we will first pick a cell that will be the root of our binary tree. And then it will have a left child, a right child. And these internal nodes will also have their left child and right child. And so on. So in the end, we will have leaves. So how these cells are arranged in this grid is kind of arbitrary, except for some criterion that I will state in a minute. Well, I won't complete the drawing. I think it's kind of clear for now. We will say that the column containing the root is a special column. We're going to call it a marked column.
Hey, what's the total size of the tree? Is filling all the nodes in this grid? Or?
Yes, so I haven't mentioned that because here in the second criterion that I want to mention is for all the other column, unmarked column, we require that each contain exactly one leaf. So that will restrict the size of the tree and probably also like n. So each unmarked column contains exactly one leaf. Now to actually encode this tree structure, we will store 2 pointers in each cell. So each cell contains 2 pointers, the left child and right child. It may not be used. For example, a leaf will not use left and right child pointer.
So every entry is really logarithmically many bits.
Yes. Yes.
The variables of the function will be these bits.
Yes. Yes.
Yeah. So the function is defined over about n squared log n bits.
Yes.
Okay.
Yes. Okay. Right. So that's 2 pointers. In fact, we will need another pointer, a back pointer, which will only be used by leaf. Will not be used by internal node, but only be used by a leaf. And its usage is the following. We are going to use this back pointer to point back to the marked column. So every leaf has a back pointer pointing back to this column.
So this is the intended use of the input, but of course not every matrix full of such information is
Yes.
conforming to the.
Sure. So this is I'm only describing 1 instances. All the other instances will be a 0 instance.
Oh, I see. Every time you have bits describing a structure like this is a 1. The value of the function of this is a 1, and every time it doesn't describe something like this is a 0. Is that it?
Yes.
Okay.
Yes. So a final thing, like I said, the column containing the root is a marked column. So this column is special not only because it contains a root, but also because for all the other cells, we require that it should be no pointer, no pointer, no pointer. So we will not use the pointers of the cells on the marked column other than the root. So that is a full description of a 1 instance. So maybe I'll give you some time to look at this picture.
So in a cell that doesn't appear on the tree, you're free to put anything? Or,
yes.
Okay. Do you have to only go down as you go to?
No. It's arbitrary.
It's just in the picture.
Yes, it's arbitrary.
So some other cells not in the marked column will also may have this bottom, null.
Right.
Yeah.
Right. So yes. So basically,
is the tree required to be complete binary, or it can be a partial tree?
let's just say it's a complete binary tree. I mean, it's kind of arbitrary how we define this thing, but let's, for simplicity, just say it's a complete binary tree.
With n leaves.
So n needs to be 2 to the
Anyway, with n leaves.
Yes, with n leaves.
Yeah, but then if it's going to be a complete binary, then n is for to be 2 to the k.
Yeah, well, if you care about the depth, yeah.
Okay, so maybe let me make some comments to help you understand this construction.
Wait, does complete binary means that everyone has 2 childs, and it also all the paths get to exactly the same level, right?
Yes.
Or it just means everyone has either 2 or 0 childs? Yeah, for me, complete binary means, there's a fixed height and then it's just one tree. Yeah, there's exactly one tree that's complete binary of a certain depth. Yeah, I thought, yeah.
Let's just say we only allow trees look like this.
Okay.
So it has like 2 to the n minus one nodes in total. Okay, yeah, now let me make some comments to help you understand this construction. So if you know where is the marked column, then you can very easily verify whether your input is a one instance or not. You just find the root and traverse the tree and to see whether this tree is a complete binary tree such that every R-marked column contains exactly one leaf.
Can you repeat what you just said?
Oh, okay, sure. So if you know where is this marked column, then you can easily verify whether your input is a one instance or not. What you do is you just find the root and traversing the tree.
So it's before even talking about randomized complexity, you can talk about certificate complexity. I mean, you would like to say, I mean, for the separation, you want to say that the deterministic complexity is close to quadratic, to the total number of variables. It's about n squared log n variable. So it's that's probably easy. That's deterministic, and you want to prove that the randomized is small. It's about linear. The very least you should do for that, by the observation before, is that you should show that the one certificate complexity and the zero certificate complexity are linear. So that's what he's doing. He's now telling us why the one certificate complexity is small.
Yes.
Can I just ask, you could have two trees like that existing in parallel to each other. Like, is that like kosher? Is the value of the function?
No, it's not possible. You can have at close to one.
So you need to have exactly one tree like that.
No, but the question is whether whatever you have is a tree like that or it's not. Right? That's the question. Then you want to certify that it is, right? So if you know where the marked column is, you could say, well, this marked column, for it to be a valid marked column, it needs to have at most one thing that doesn't have three nodes. And then you can just follow and say, well, once it does, right?
No, but there can be another disjoint tree.
No, because then you would either see its root in the marked column or you will not have a leaf in every other.
He was not testing that that's the only root in the marked column. He just started from some root. Or what is exactly the certificate? You go over the whole root.
Yeah.
The whole marked column, or you
Yes.
you query all the column, all the marked column.
Yes, all the marked column
Okay, good.
and all the nodes in the tree.
Okay.
I thought like in the nodes which are not part of the tree, you could just have garbage. And
You could have garbage.
It doesn't affect the
But
value of the
it's fine to
function.
query the whole column and the whole tree. You're gonna get n, right?
Yeah.
And the input size is n squared, right? N squared
You
log.
see that there's a leaf in every other column. So this means that no other column can be marked as well. And in the marked one, there's only one root.
yeah, for this tree, but there are two trees like this would exist.
No, so it's
No,
not
no.
any other.
But you want certificate, so it doesn't matter if
No,
they're.
I'm one step behind all of you.
Sure.
I don't
So let
understand
me-
what are the rules for the
Yes.
function.
So let me just tell you,
One.
you cannot have, you can have another tree, but the thing is, you can only have one marked column, so you can have.
No, I guess, so his question is before. The function is defined like this. You can take a matrix that can describe anything. If it does describe a tree like this.
And
the
only
value is
one.
No, any tree that looks like this. If it does describe a tree that looks like this, then the value of the function in this matrix is one. If it describes
Okay,
something
now
that
we
is not
answered my
valid,
question. Okay,
if it describes something that's not valid, then it's a zero.
okay.
But notice that if it does describe a tree like this, it can describe only one.
Yeah, but it's not important.
No, but I think this is what he was asking.
Well, anyway, it's not important
No.
for the argument.
There are multiple trees that look like this, right?
No, you're asking the same
So
instance.
what I was saying is that if an input is valid, it describes exactly one tree.
Why can't there be two valid trees with different marked columns?
Because
No, you can have multiple.
yeah,
You can
okay.
have multiple trees even with the same mark column, right? Because if the mark column points to a different cell, then it's a different
You
tree.
can actually know which one is a leaf. This is I guess what I. Okay. You can actually know which one is a leaf, but like it could be, okay, what I thought is, it could be there are some other cells which are behave as leaves, but they're not connected to anything. Nothing points at them.
Yeah.
This does not affect the value of the function.
Yeah, the function is still 1, as far as I understand.
So maybe let me just
Continue, sorry.
maybe let me just say just emphasize that there will be only one marked column. So basically, we want that like for one column there's no leaf, and every other column there is exactly one leaf for one instance. Okay, and now another comment that I should make is these back pointers. It's like help you to find the marked column, but somehow they can only help you in the randomized algorithm. Not much helpful in the deterministic algorithms.
It just proves that C1 is about n log n, right?
Yes. Yes. I can tell you why the deterministic complexity is large. So by standard adversary argument, let's call this function Tn.
Just say at all why the randomized complexities? No, because for the one
not
certificate.
yet. It
Okay,
No, not yet.
one certificate is clear. The 0 certificate is a little bit more complicated.
Yes, but still, we will see the algorithm in a minute for randomized query algorithm. So first, we start from the deterministic complexity, and the claim is that you need to query n-squared cells. So with almost generality, we will say that when we make a query, we actually query an entire cell, which gives you more power. But still, we will prove this n-squared lower bound. And as I said, this is just a standard adversary argument. And the adversary strategy is the following. Like when you make a query into some cell, ij, the adversary will check, like will count how many queries you already made into that column. If you have not invest a lot of queries, then the adversary will try to trick you and motivate you to invest more queries into that column by
answering null.
Yes, by entering null pointers. The qj is small. Return the null pointers. And if you have already invested a lot of queries into that column, now the adversary can laugh at you. Yes. Say, this is a leaf. But what he will do is he will try to make a leaf pointing back to every possible column. So he will make a leaf pointing back to the first column, a leaf for the second column, etc. So to implement this adversary strategy, if the number of queries on this column so far is less than, I guess, n.
And yeah, that's why you pick 2n.
Yes. then you return this null pointer, and if it's greater than n, you return the bottom and qj minus n plus 1. So it's building some number so that it goes from 1 to n.
And you don't know which one is the actual leaf because you don't know which one is pointed at.
Right. So that's the adversary strategy. And then the claim is that if you made, say, less than n squared queries, then the data can be completed into a 1 instance and can also be completed into a 0 instance. The first, it can be completed into a 0 instance basically because you can ruin all the columns. So we just look at how it can be completed into a 1 instance. So
Can you repeat why 0 instance? Can you repeat why it can be completed to a 0 instance? Just repeat.
Oh, just ruin all the columns. So some of the columns that you have invested a lot of queries, they already cannot be a marked column because of this back pointer. And then for other columns you haven't invested enough queries, there will be unused cells that you can put some back pointer there.
Oh,
So it will not be a marked column. So it's easy to make a 0 instance even after you made like a SQL query. And then you can also make 1 instance. This is because like if you only made less than n squared queries, then for some column, you will not be able to make enough progress to see a potential leaf. So you can complete that column into a marked column. Yes, and now for every other column, either you have a lot of queries, so there will be a potential leaf pointing back to this column, or there will be unused cells for you to use as the leaf to pointing back to this column. And just notice that because in total you have like 2n squared cells, and up to this point, the number of cells we see is like n squared. That's the queries you made, and maybe linear number of cells that you used for leaves and for the marked column. So you will still have enough unused cells that can be used to make an internal node. So that's how you complete the input into a 1 instance. As I said, you can also complete the input into a 0 instance. Therefore, if you only made n squared number of queries, you cannot know the value of your of this function. Okay. Yep. So next, let's see the randomized algorithm. So for the algorithm,
So before the randomized algorithm, so you showed us one certificate is just linear in log. And the zero certificate is also something like this, because we can either find that we can either prove that no column is marked by finding a bad entry in every column, or find a marked column and then explore the tree and see that we get a contradiction.
yes.
Yeah, so that's we have small one certificates and small zero certificates, and a randomized algorithm must just show that we can, by sampling, reach such certificates without can identify, right? I mean, so the randomized algorithm will will just by sampling will find.
Yes.
Yeah. Okay.
Yes. Right. Yeah, but the thing is how you sample a certificate.
Zero.
Thank you. Well, there isn't much you can do. So what you are doing is you are like repeatedly sample a column. Zero.
No. In the statement. Right? Not only.
Oh, yes. Yes. So let's just say, let's put an arbitrary number here. But in reality, it will stop in logarithmic number of iterations with high probability. So in the first round, you just query the first column. All the cells in the first column. And if you're lucky, this is a marked column. And then you can you basically find the certificate. Just verify. So the more interesting case, when it is not a marked column, you will look at the cells, and some of the cells will be a potential leaf, pointing back to some potential marked column. So you take a list of the potential marked column. So in the next round, you want to, how to say this? So in the beginning, this list can be very large, can be of order n. And what we want is we want to like try to find a promising potential marked column. Promising in the sense that if it is not a marked column, then in the next round, the size, the number of potential marked column given by that column will be smaller. So let's see. So what you will do is you will like check the columns in this list Lj, and you will sample a few cells in that column. How many of the samples you can use? I claim that you can use 2 to the I is the round, the first round, the second round, the number of iterations you go so far. Times say 100 again cells on this column. Now, if you, in this sample, if you see a violation, so if you see something that contains a marked column, that contains a back pointer, then you immediately know that this J prime cannot be a marked column. But if you didn't see any violation of our requirement on the marked column, then this is a promising column. You can use it for the next round. So let's just say
So the point is that you can allow yourself more samples as you proceed. This 2 to the I is growing.
yes,
Because the list size is shrinking by the same amount.
yes.
So the product of the list size and the number
Yes,
of
yes,
samples
yes.
is still linear all the time.
Yes, yes. So I claimed I claimed that we can sample this many cells. Why? This is because if your column J prime passed this test, it didn't see any violation. It can be a marked column. That means basically, except for maybe one cell, which is a potential root, every other cell you see is just bottom, bottom, bottom. But if there are a lot of like back pointers, if there are a lot of potential cells in this column, then you should be able to sample it with high probability. So in particular, with overwhelming probability, Lj prime, so the potential leaves for that column will be smaller than n divided by 2 to the I. So that justifies why you can use this many samples in the next round. Yes. Well, some of the details of this algorithm is missing, but I think at this point it already gives you the idea why the randomized algorithm without error has more complexity. Any questions?
It's really clever.
Yes. Yes. Any questions? Maybe I just go over it again. So what we will do is you will just repeatedly query a column. In the first iteration, there's no information, so you just query any column, say the first column. And the lucky case is that you find the marked column, then you just verify from your marked column. Otherwise, by looking at this column, you collect some information. So some of the cells will be the potential leaf cell. Some cells will be some junk. But then by looking at the potential leaf and their back pointers, you know what are the potential column. In the beginning, this potential column, marked column, can be very huge. but we were trying to refine it more and more. So what we do is we sample some cells from that column, and we see if there is any cells that has a back pointer. If that's the case, then this column cannot be a marked column. It will not be a promising column for you to check in the next round. But otherwise, you not only find a column for you to check in the next round, but also you know that in the next round, the number of potential leaves in that column will be smaller with high probability. So basically smaller by a factor of 2. That also justifies why, like after logarithmic iterations with high probability, this algorithm will end.
After logarithmic number of iterations, we will afford to query the whole column.
Yes.
We expect to be.
Yes.
Yeah.
Yes. Any questions?
Is it important that when you sample the cells in these columns that you keep track of what you've sampled in the past, or does it work even if you just flat off?
It doesn't matter.
Yeah, I imagine that it didn't matter. That you can sample, even if you sample the same cell again, it doesn't matter.
Yes.
It's growing. Oh.
Hey, it's up to you, but you can take like a 5-minute break. Because I mean, whenever it's convenient to the.
Sure. No. It's okay. Maybe let me finish comparing deterministic versus randomized query complexity. Then we take a break. Okay. Okay, so let me make a summarize by drawing this picture that you can look at during the break as well. So we studied the relationship between the zero-error randomized query complexity and deterministic query complexity, and we showed that deterministic query complexity is upper bounded by zero-error randomized query complexity squared, and this quadratic separation is achievable. Then, if we put randomized query complexity with bounded error into this picture, so let me make some few remarks. So first, Carney all proved that the zero-error randomized query complexity is upper bounded by the randomized query complexity with error squared. And this bound is also tight.
For that, there was a cubic bound, right? I mean, the previous.
Before this, there is a bound which is like r squared log n, and also there is this cubic bound. But
I guess, okay, maybe I just want to say that between D and R, there was a 5th power. Oh, yeah, for many years. Yeah. For now.
Oh, okay. Yeah.
Yeah, 35 years ago.
Okay. Yes. And right side, basically, you use some variations of this pointer function, also due to minus at all. So that left us with this pair, the randomized quadratic complexity with error and the deterministic quadratic complexity. So what we know is that the deterministic quadratic complexity is upper bounded by randomized quadratic complexity raised to power of 3. The proof is easy, so let me just tell you. This is because we said earlier that the deterministic quadratic complexity is upper bounded by the zero certificate complexity times the block sensitivity. I didn't prove this, but I made a comment there. And then the certificate complexity is bounded by the sensitivity times block sensitivity. And why this is the case, you just take any input and say you have these blocks, minimal blocks, minimal with respect to set inclusion. That achieves the block sensitivity of input X. So by which I mean flip this block of variables, you also change the value of your function. And then the claim is that each block will have size at most the sensitivity of your function.
Well, otherwise, we could make it smaller.
Yes. Otherwise, you can make the block smaller. Yes. So if you take the smallest possible block, so smallest in the sense of set inclusion, that means if you look at the input Y, which just look like X, but with some block flipped. We flip this block. And then you will realize that by flipping any variable inside this block for Y, you also change the value of the function. Therefore, by the definition of sensitivity, the size of this block must be smaller than SF.
Maybe I should say that many of these arguments go back to normally some thesis who really started this study and made many of the both results and conjecture, defined block sensitivity with sort of an obvious measure and also sensitivity conjecture, which have just recently resolved. It all goes back to the mid-80s in Berkeley.
Yes. Yes. So I think that this is by Nissan. And then I claim that this is at most the randomized quadratic complexity cube. Well, the reason is simple. It's because that block sensitivity will be a lower bound for randomized quadratic complexity. Because, like for example, just look at X and Y with the first block flipped, then a randomized algorithm should be able to distinguish these two inputs. To distinguish these two inputs, you have to make query into this block with high probability. So this is a cubic upper bound.
But it's still not clear because it's not clear what the relationship, by sampling. So it has to look at each block with high probability.
Then by linearity.
But what is the... So it seems like it's 1 over, like n over the block sensitivity. What's the probability that...
Like 1/3. If you need to, so if your error is only like 1/3, that means your algorithm, the difference that your algorithm, how to say, the expected value of your output evaluated on y and the expected value output on x will be greater than a third. Yeah, because 1 is greater than 2/3, 1 is less than 1/3. So their difference will be greater than 1/3. But to have this difference, that means you must visit this block with probability at least 1/3.
Yeah.
Yes, so like probability of I, that is the probability that you visit the block I, which is larger than a third. And if you have this many of blocks, they're like summation.
So just linear expression.
Yes, yes, yes. Any questions? So maybe let me just finish this. So I'm saying that because your algorithm should be able to distinguish x and the block flipped. Therefore, the expectation of the output evaluated by your algorithm on y should differ from the output evaluated on x. The difference will be large. That means the probability that your algorithm visit this block is at least this large. And then by linearity, your algorithm should, the algorithm that you visit, the number of queries of your algorithm will be at least the expected number of queries you made to each block. So that is like block sensitivity divided by 3. So that justifies the last line. Okay, so what about the other part, the separation part? What do we know? Well, the larger separation is the one you see. I guess closing this gap is the open problem here. And let me make one more comments. The comments is
So is the lower bound this function or?
Yeah.
yes, yes. So it's just yes. Because randomized query complexity is smaller than zero error randomized query complexity. So this separation directly becomes the separation here.
What about in the Kulkarni tau? Oh, it's a different example.
It's
It's a different example, yes.
So it's similar. No?
Yeah, it's similar.
But it came in 13.
Oh no.
No.
That's the upper bound. That's the upper bound. So yeah, that's the upper bound.
I said on minus it on it. Okay. Yeah.
Yes. So the separation is given by minus. Yes. Yes. So the comment that I want to mention is that this cubic upper bound comes from the fact that the deterministic query complexity is at most block sensitivity raised to power of 3. And the largest separation between deterministic query complexity and block sensitivity is quadratic. So there is this conjecture saying that deterministic query complexity is in fact at most block sensitivity squared. There's just a conjecture. I think now it's a good time to take a break.
Okay, great. Okay, so 5 minutes. Let's do it.
You know this tau, do you know what's his first name?
Avishai.
Yes.
Oh, okay, it's a different tau. No, because I know a tau from that took the same undergrad as me, which is
Oh.
it's a
Last name Tal or first name Tal?
last name tau.
Really?
It's
What was the first name?
Fabio.
So, say again?
Fabio. But he works in dynamics. That's why I don't think it's the same person.
By Israeli?
No. Well, he's Brazilian. I don't know.
Brazilian, no, it's Avishai is Israeli. Tal is a common. It's both common first name and common last name.
Oh, I see.
Tal is dew,
Oh,
like the morning dew on the grass.
Oh, dew.
Yeah. I never saw this in detail. It's very nice. The example. I mean,
Sorry, which?
This embedded binary tree. I mean, I've seen the goose thing, which is for communication complexity, and this is very, very nice.
Yes.
What about, like, could it be that D of F is at most the sensitivity square, not like stronger conjecture instead of block sensitivity?
Block sensitivity is smaller than sensitivity, right?
No, block sensitivity is not.
It's bigger.
Harder.
Block.
You can have more blocks.
Yeah.
Sorry, yeah.
So is there a counter example to changing the block sensitivity to sensitivity?
Yeah, actually, I can't recall. I'm not sure, but this you can check very easily. I'll tell you like later. Let me see. Yeah, I don't remember.
Somebody's name, RBJ, yeah.
Yes.
Yeah,
Have you thought about making that construction three dimension instead of two dimension?
No. Yeah, I think in the so there is a problem, well, which we will see, and that is open, and I feel it's promising by just looking at this pointer technique.
you think that making it three-dimensional will make something
in the separation, because there is a cubic.
Wait, what is the tight example for the separation between R0 and R?
R0 and R, okay. Okay. So that I can make some comments. So it's kind of variation of this construction. So you need to make a lot of adjustment, but I think the key idea is that if you remove half of the back pointers, you remove half of the back pointers. So half of the leaves will have the information help you to go back to the marked column, and half of them will not help you. Then it will ruin your algorithm for zero-error randomized case. But for randomized case, you're fine. You can still do something.
Well, I assume Vijay is coming back. We will pick up.
Yes. Yes.
Okay.
And honestly, the start part of the second half is exactly because I'm going to introduce you what is quadratic complexity for completeness, and then I'll tell you this spectral sensitivity. and then see the connection of this sensitivity theorem with this query complexity. So let me just start by briefly reviewing what is quantum query complexity. So now we are going to pick Q into the picture. For quantum query complexity, we need to discuss like quantum state. So let's say we have a quantum system of some quantum bits. Then the state, we will describe its state by a vector in a Hilbert space. So say we're going to present a state in this vector space C to the m. So a 2 to the m dimensional vector space.
This will represent m qubits.
Yes, this will be used to represent m qubits. So in particular, for any m string of m bits, so that corresponds to a classical state of m bits. Then there will be a vector, a unit vector used to represent this state, this classical state. And so these classical states are different. In the linear algebra language, is that they form a orthonormal basis for a vector space.
We can think of them as the unit vectors, the standard basis of this 2 to the m dimensional space.
Yes. Yes. Okay. So now a general system containing m quantum bits can have superpositions of these classical states that will just be represented by a linear combination of these bases. And additionally, the length of this vector is again 1. And the reason is because we have this interpretation saying that of the absolute value of alpha x squared, then that is the probability you see x when you measure your quantum bits. And we will call these things in the linear combination as amplitudes. So that is how we represent a state in quantum system. And then let me tell you what is a query operator. So when we make a query, what happens? What you will do is you will prepare your quantum system, the bits, you prepare your bits into a query index. So meaning that you want to know xi. And when you apply this query operator, it will tell you xi, but it will put this -1 to the xi into the amplitudes of your quantum state. So in general, this operator extends to the entire space by linearity.
It's a bit confusing that beforehand the indices were x, and now x is really the input to the function f that we are trying to.
Yes, yes.
So it's,
Maybe I just use I here.
yeah.
Anyways, okay, and then an algorithm, a quantum algorithm.
Now what's X over
what's
there?
X? I don't understand you yet.
Okay, okay, query. So now X is your input. Let's see, query. So like classically, when you want to query something, we visualize it as a decision tree. Like in each node, you have a variable that you want to query. And quantum.
I just don't understand the notation. What's -1 to the power xi? What's x sub I here?
It's a bit in position I. X,
But I was not a position. I is the entire vector in -1 to the m.
No,
yeah, but it's a name. It's a name of an index to a vector of length n in this case.
Yes, yes. So when I put like cat I, it represents some vector that corresponds to this classical states of I. So it's just so I and cat I are different. Cat I is a vector. I is a number here.
So maybe
I here is just between a number.
between 1 and n.
Okay. You change it back there to I, which completely.
Yes, so m is log n maybe. M is log n in this case.
Yes, m is log n. Yes.
M is log n.
Okay. So what?
So
Okay, so X is in 2 to the m.
X is 0, 1 to the n.
Okay.
And n is 0, 1. No, to the n.
No, it's
It's 2 to the m. Right?
It's 0, 1 to the n, and
yes,
n is 2
okay.
to the m.
Yes, yes.
I is an n, right? But you're encoding it in bits.
Yeah,
Yes.
you can. I mean,
I don't know what is a good way. Maybe big M.
so you can run it's 2 to the m. Yeah, we have a function x is an input to a function f that we want to evaluate. Okay. And the intuition, I mean, you can ask yourself why is there no decision tree version of the quantum algorithm, right? I mean, we have a decision tree version for the deterministic case, we have it for the probabilistic case. We don't have it for the quantum case.
So what's the reason for the input being 0, 1?
What do you mean?
No, really, it's fine if you want to use -1, 1.
Or no, I mean like real numbers.
We are talking about the function we are trying to compute always in all this discussion is some function f of x, right? We try to evaluate a Boolean function. Just a function of IQ. So we didn't change anything. It's just a deterministic algorithm. The query is, tell me what is in xi. Probabilistic algorithm gives you a distribution and tell me, I pick this from this distribution. In the quantum case, you want to say superposition of the i's, but you cannot make a decision. You don't really want the result. You want to keep you don't want to measure the result. You want to keep the superposition. So you'll get cancellations and all the wonders of quantum computing. That's why you have to represent it this way.
Okay. Thank you, I guess.
I would also say at this point, it doesn't really matter that you are encoding that with bits. It might as well as been just n, right? You're just working at space c to the n for some n.
Yeah.
Right? There's no reason to encode by bits at this point. Later on, might be important.
No, it could not be important.
Well, okay. So any like more confusion about this definition?
Yeah, what Leo was suggesting is that, you know, I will simply range over n.
Yeah, one
Yeah.
number between one and
Yeah,
n.
well, number between 1 and n, and we are working in the
Yes,
Hilbert
yes.
space of C to the n.
Oh, yes,
And we
yes,
don't
yes.
have to think of them as bits. It's, you know, maybe.
I mean, unless you're talking about like, bases of computation. then
Yes,
that's-
yes.
If you're not gonna talk about that, might as well. simplify it.
Yes, yes, yes. True.
I guess it just loses the analogy to classical bit strings.
No, it's.
No, but
it's-
even in classical, you typically think as n, unless you need to encode something, then you say no. And you can encode it, but
Right, it's a good suggestion. Unfortunately, I decided to
That's okay.
use this notation. Anyway, so now let's move on to quantum algorithm. So normally you just start with some initial states. Just have your quantum bits initialized to be 0, for example, and then you can do some preparations, meaning you're doing some computations on your quantum system, which by quantum mechanics, it should be a unitary operator.
I mean, there's also a semi-mathematical motivation. If it's not unitary, it will not preserve the probabilities add up to 1, right?
So you need to preserve the orthogonality.
Yeah, right. So because
Yes, and
there will
also-
be an interpretation of probabilities.
Yes, and also you don't want to ruin the length. Yes.
It's not just a unit, it's not just the norm, it's the orthogonality.
Yeah.
Yes, and after you like did some preparation, you can make a query, and now you collect more information. You can do more computation. And so on. So in the end, when you output, you just query, you just measure the first quantum bit. This is without loss of generality, actually. Don't worry about it. So to output,
Maybe you should stress these UIs are not dependent on the input.
yes,
They're just fixed unitary matrices.
yes. So you. Yes. Okay, so to output, what you do is to measure the first bit, and mathematically what happens is you output 1 with probability, which is just sum over okay, I think that's why
Yeah.
I want to use this quantum to the end. So here we want to make sure that we're summing over all the amplitudes corresponding to the first quantum bit is A1. That's the probability you output 1. Well, I guess at this point, it's just some abstract definitions. If you see it for the first time, you won't have any feeling. So let me give you an example, maybe illustrating the power of quantum algorithms. So the algorithm is well known. Choose algorithm. And the problem here is your inputs x comes from two cases. So in the first case, it's either the all zero input or all one input. And in the second case, x has equal number of 0 and 1s. Well, maybe I should use n.
All right. Oh, you call this capital M.
Yeah.
Let's call it M. No, it's a capital. It's the length of the input.
Yes.
You can call it M. I don't know why you call this capital M.
I just want this correspondence
Okay,
to be clear.
yeah. So it's a partial function. You don't care to know what the value of the function is in either, but maybe in case 1 you say 0, in case 2 you say 1.
Yes, so this is important comment. And we will see. So you can see that for any deterministic algorithm, you basically need to query all the bits. You need to require at least m divided by 2 plus 1 bits. But now I'll show you that using a quantum algorithm, it can be this cases can be distinguished using just one query.
Same also as a fast probabilistic one.
Yes, yes, I have to admit, but I think this is the simplest example to illustrate here.
Essentially, what the quantum is doing is what the probabilistic one is doing. Only you can like take expectation on one query, right?
No. I want to present it in a way that you are using the power of unitary operator. So the one query algorithm is the following. First, you prepare quantum states to be the superposition all possible query indices. So it needs to be a unit vector. So we have this term to normalize it. And then we make a query. So maybe let me just remind you, this is just a vector. If you write it in the standard way, then in the first case,
I don't think this is reasonable. This color
this is not okay. Let me use a different color.
Probably one. I mean, you didn't do the query, the right hand form of the query. You know,
You forgot the minus one.
minus one to the.
Yes. Okay. Here I want to just remind you that these are just vectors, and let's just write down what you would normally write for a vector. So in the first case, after this query, what you will have is a vector which is this O1 vector with probably plus minus and 1 over square root of m in the front. And in the second case, what you have is this vector that has half its entries 1 and half its entries -1. And now we want to apply a unitary operator. Actually, any unitary operator such that its first row is all 1 divided by square root of n. For example, Hartman matrix would be a unitary operator satisfying that the first row are all the same. And then you realize that h times the state here in the first case. What you have is a vector whose first entry is either -1 or 1. So because the row and this vector is fully correlated, and all the other entries will be 0. And now in the second case,
This is by unitarity.
yes, all the other entries are 0 is by unitarity. And in the second case, what you have is the first entry is a 0 because this vector is orthogonal to this row. And the other entries, whatever they are, we don't care. Now, if you measure this quantum system, if you measure all the quantum bits, then in the first case, what you observe is, so this is just all zeros. And in the second case, some of the quantum bits will be a 1.
So you change the notion of an algorithm rather than measuring the first bit, you measure the whole system.
Yes. So this is without loss of generality, but let's don't elaborate it here.
Yeah, so it's a little better than the probabilistic algorithm because you get disjoint inputs. I mean, right?
So no, yes.
Right, it's a little better than what a probabilistic algorithm can do because you will never get confused.
Yes, you won't make an error. Any questions? Okay. I assume there's no questions. So next, I want to tell you about this spectral sensitivity.
So maybe before you are not going to talk about Grover.
No.
Okay, so just one comment. I mean, this is not a very interesting function because it's a partial function. We are interested in the complexity of total function. And the first really interesting non-trivial example is given by Grover for the O function. The O function is a total function. To compute it with deterministically or even probabilistically with constant error, you need n queries. I mean, if there's a single one, the chances you'll find it. Yeah. And he gave a quantum algorithm that does it in root n queries. So that's a quadratic gap, and that's what started the thing going even before Shor's algorithm. So
Yeah. Okay. This is a notion that may be familiar in your view. To define spectral sensitivity, we need to first define the spectral graph, the sensitivity graph of the function f, whose vertices is just the inputs. And the edges are those inputs such that they differ in exactly one location. And and they have different output in your function.
There's a subgraph of a cube connecting the ones to the zeros.
Yes, yes. And then after we define this graph, you will have an adjacency matrix. And the spectral sensitivity is just the spectral norm of the adjacency matrix for the largest eigenvalue. Okay. And then what Romson and David Kothari observed, proved based on the result of one in the following. So which will be a crucial to the relationship between quantum and deterministic complexity, which we will discuss after I finished telling what is this theorem. So it says that the spectral sensitivity is lower bounded by the degree of the function takes the square root.
Is it a degree or approximate degree?
Hmm?
This is a degree, not approximate degree.
No, not the approximate degree. Degree. Now let me make some remarks about this spectral sensitivity. First, it is a lower bound for sensitivity. So basically just notice that in this sensitivity graph, in its adjacency matrix, each the number of ones in each column is the sensitivity of that input, and then you can deduce this inequality in a straightforward manner.
By plugging the constant function into it.
Sorry.
So you deduce it simply by plugging in the constant vector into the right.
By plugging the eigenvector.
Yeah, the eigenvector you can. Yeah, but the eigenvector. Okay, I mean, if you plug the constant,
you take the constant vector and
Constant.
you compute the one inner product A1 and divide by the norm. That's a lower bound for the maximum eigenvalue.
Okay.
right?
Yeah.
Yeah,
Sure.
that's how you deduce.
Yeah, sure. Okay, so from this and the relationship to the degree.
Wait, I think it's the other way. What you like that would be like the lambda of f would be an upper bound for what happens when you plug in the constant vector, not a lower bound. I think you really need to use what is this theorem called for matrices, saying that if all the entries are positive, then yeah, exactly. You really need to scroll from
you need the non-negativity.
It's not just plug the all ones.
No, you're right. You need the non-negativity.
Yeah.
So you're very good. Yeah. Of the matrix entries. Yeah.
Okay. Well, anyway. Anyway, so this you can do. And second remark is that the quantum query complexity lower bounded by this mirror as well. So this requires some background, so I wouldn't explain it. But now from here, what we can say is that we can now compare quantum query complexity versus deterministic query complexity. So as Avi mentioned that the largest separation that we know is due to Grover. It's a quadratic separation. So historically, what we know is there exists function such that the deterministic query complexity is quantum query complexity squared.
Hey, sorry, I actually missed. So in the top board, you have x equals yi. Is there an I missing, or what am I missing there?
Wait, what? Here?
Yeah.
It's a subgraph of the Hamming cube, right? You look at the Hamming cube and you keep only the edges where the function flips.
Why is
Look at the Hamming cube graph, right?
I
I only have edges that differ by one.
It's not y sub I, it's y sub I.
Ah, yes.
And
Yes.
flip the I bit.
Oh, okay,
Yeah.
okay. Sorry. Okay, yeah. So yeah, it's only the edges where they disagree after one bit. Okay.
Why do you compare it to the deterministic complexity and not to the randomized one?
Well, we will do that, but let's start from deterministic query complexity. That's the I think it's a reasonable order, deterministic and then randomized.
Just because quantum query complexity is inherently randomized in a sense.
Oh, I see your point. Yeah, okay, sure. But here the reason is because you will see that we completely understand the relationship.
Yeah, the question is whether you can get a bigger gap than quadratic, right?
Yeah, that's
For randomized, we know that or for randomized, but
just saying it's a weird comparison because you do have randomization and error in the quantum query complexity. So comparing it to something deterministic, not to the random.
yeah. So, but it's potential that the quantum complexity can be logarithmic in the deterministic one, whereas we know that it cannot be massive, right? I mean, well, anyway, it's a good question to ask.
Yes, but I mean, like, we also ask BQP versus polynomial time, and one is probabilistic, one is not. So I don't see the problem here.
We should ask all questions.
It should be BQP versus BPP.
Yeah, your question is also good.
You do this one first because D comes before R. That's what
Yeah.
Okay. Yes, and historically, the upper bound also comes from the fact that deterministic query complexity is upper bounded by block sensitivity raised to 3.
Sorry, can you explain the diagram you just did? What was like this Q and D and what
Well, I'm just
say here?
Just comparing these two measures.
Okay.
And I'm saying that historically, commented by Avi, that Grover showed this quadratic separation, which was known to be the largest for a long time.
Okay.
And then we also know that the upper bound is like quantum to the 6th power. And this also comes from the fact that the deterministic query complexity is upper bounded by the block sensitivity raised to power of 3. And then block sensitivity is upper bounded by quantum query complexity raised to power of 2 that I wouldn't explain. This is basically due to reveals.
Does it use spectral sensitivity at some point?
No, not at all. So this spectral sensitivity is really new.
Yeah, sure. Okay.
Maybe 98, I don't remember. Well, and then the pointer function that you just see actually give us a quadratic separation. So you just convert that randomized arbitration into a quantum one. You get another quadratic speedup. Now what?
Maybe you can point out, I mean, the way you convert the randomized to a quantum, you realize it's the randomized algorithm that shows us for this, pointer jumping. It's about just computing an OR function, just hitting something you would like to see.
Yes.
And when you see it, you recognize it. And for OR, the OR function, we have Grover's result, which is another quadratic speed up, so you get a four-way, yeah,
Yes.
4 power.
Yes. Yeah. And then I think somewhat remarkably, this is tight. That just follows from the above theorem because so what I mentioned earlier is that deterministic query complexity is bounded by degree of your function times the block sensitivity of your function, and then degree is bounded about by spectra squared, which is at most which is bounded by quantum squared. And the block sensitivity is also upper bounded by quantum squared. So that's how you get this upper bound.
Can you clarify those references again? Why do you have 2 references up there with, next to the sensitivity theorem? The ABKT and Huang, can you just clarify who did what?
Oh, I see. So the proof is essentially Huang's sensitivity theorem. But Ronson et al. They adapted Huang's proof and realized that this is actually a lower bound of quantum query complexity.
Huang doesn't directly talk about the degree. He has all the ingredients. I mean, he's defining, he's making the connect. He defines essentially the spectral sensitivity.
Yes.
And uses it to argue a relation between sensitivity and block sensitivity.
Yes. So in Huang's work, he is considering this combinatorial problem of like induced graph on Boolean cube, and in Ronson et al.'s work, you need to translate that language into computer scientists.
Wait, so remark 2 was made where, and is it like how
This is just a remark I want to let you know, and this is also like observed by Ronson.
So this is easy to see.
If you know the background of quantum query complexity, it is so you need to know the adversary lower bound for quantum query complexity, but we won't have time to discuss it. Yes, so if you know that lower bound technique, then it's straightforward.
Does it use approximate degree?
No. It's a different technique. Okay, and I think a third remark that I want to make is that Well, it's about some specific problems. So we know that the degree of the monotone graph property is n squared. This is due to this and the Conan. And therefore,
you should say also write down what f is for every monotone graph property.
Yes, so f can be any monotone graph property.
Like you think of connectivity or bipartiteness or whatever, any graph property on the vertex says if you want to, have a real function describing it, then it's basically you have to the degrees about the total number of edges in this.
So this implies that the quantum query complexity is at least order of n. Sorry, n is the number of vertices.
It's polynomial n squared, so there's a lower bound.
Yeah, it has maximum degree.
Okay, so then it's I guess, non-trivial monotone.
Yeah, non-trivial.
Oh, sure. Of course, non-trivial, yes.
Also.
Yes.
Yeah,
Okay, so that implies that the quantum query complexity for any non-trivial monotone graph property is at least order over n, which is tight because whether there exists an edge in your graph is a non-trivial monotone graph property, and you can apply graph search to find an edge in order of n queries. So this also implies that this theorem is tight, this inequality is tight. Okay, so I guess we want.
So by graph property, you mean something that is isomorphism invariant.
yeah.
Okay.
Yeah, okay. So we won't have time to look at this theorem. Let me just finish by summarizing the relationship between quantum and other complexity measures. So the relationship between quantum and deterministic query complexity is now settled. If we compare quantum versus like zero error randomized complexity, then there is a cubic separation, and the upper bound, this quadratic upper bound were applied as well. So let me just say it. So also zero error randomized query complexity is upper bounded by multi-query complexity raised to the power of 4 for some reason. And the largest separation that we know of is cubic. This is also
This is 3, this 2. It's a 3.
Yes, it's a 3. It's a 3. This is also using the pointer technique. And then we can compare quantum versus randomized query complexity with error. And the upper bound is again quadratic for the same reason. And the lower bound, well, you may think also by the pointer function, but actually no. So here it's a complete different story. We also have a cubic separation. And this story will be the topic of the next seminar. Okay. Any question?
Well, yeah, thanks. Well, now is a good time to question. Questions for the audience.
Is there any average case theory for all of these things? I guess it does make sense to ask these questions like complexity for a typical input X.
For the uniform.
For the uniform.
No, yeah, these are studied for various.
It was studied.
Yeah, so I mean, it just you can think of graph properties as a good example. You want to know how many queries you want to determine. So this was looked at, and in fact, there are connections between some average case complexity and worst case complexity in some cases, including in.
Like all the examples here were, I mean, just a trivial function in the average case, right? They all have, like all the examples.
Yeah, they are always
very small measure.
Yeah. But as I mentioned before, I mean, the randomized query complexity is equal by minimax. Let's say the zero error randomized complexity by minimax is equal to the average case complexity of a deterministic algorithm against some distribution. Not necessarily the show. So this is used a lot in lower bound. So that's a reason to study average case complexity. And often when you are proving this, the measure you pick is uniform, or at least the product distribution. So these things are studied towards proving lower bounds on randomized decision to the complexity. So you study it and you use it usually to prove randomized lower bound. More questions? Thanks a lot.